it turns out the basis of RNA, the bases, the nucleotides that are the basis of RNA actually have been seen in comets and other places. And so we're beginning to think of ways and environments where those things can form. And then it turns out, you'd think it's that forming complex molecules is disfavored, if, in a thermodynamic sense, that, you shouldn't, forming complex things seems to be disfavored. But in exotic environments, like on comets and the presence of ultraviolet radiation, it turns out in certain complex environments, it's been discovered that actually reactions get driven toward forming complex molecules. The sort of relationship between time and space flips inside a black hole. Space has a single sort of unidirectionality. You always are moving towards the singularity, never away from it. No matter what you do, you're always moving forward in space and inside of a black hole. So that space has a very time-like character inside of a black hole, whereas time is the opposite. If you think about, life has a metabolism and it reproduces relatively faithfully. As I say in the book, you can think of fire. Fire satisfies all of those things.
Hello and welcome to another episode of the KVKurious Podcast. Our guest for today is Professor Maxwell Krauss, who is Professor of Physics at the Arizona State University. He's the host of the Origins Podcast, a well-known physicist, physics communicator, and author of many books centered around origin of matter, our understanding of life, matter, universe, and much more. This conversation is extremely thought-provoking, where we try to discuss what are the opportunities, what are the possibilities that lie ahead of us in our quest to understand how did it all begin. So listen to this conversation with Professor Lawrence Krauss on the KVKurious Podcast. Hi, Professor Lawrence. Thanks a lot for being on my podcast. Super excited to speak to you about what's happening at the helm of physics, at the center of us understanding universe and much more.
Well, it's nice to be with you today.
In 2012, you were of the opinion that string theory might be fascinating, but it does not have, or at least has not proved anything for us to really say that we've improved our understanding of the real world. Has your opinion changed in 10 years?
Well, I don't think that's quite what I said. It has improved our understanding of the world in the sense that the mathematical techniques that have been developed for string theory have been useful in various areas of physics. And a lot of fascinating ideas have been developed in string theory, holography and other ideas, but we don't, so as a discipline, it's had a positive impact on physics. It hasn't, however, yet definitively addressed the key questions that it was designed to address, or at least convinced us that it has. It hasn't yet been clear that that string theory in its original version or any of the new versions is indeed a description of reality when it comes to the unification of quantum mechanics and gravity. And so that's not clear yet. And it hasn't yet addressed the fundamental problems that it had hoped to address in that regard, to demonstrate that that the world that we see would arise out of it naturally, that you could explain things like the cosmological constant, the energy of empty space, lots of uncertain things that are mysteries, and which I discuss in my new book, in fact, are not clearly addressed by string theory. But it is, a lot of smart people have been working and have developed a lot of interesting techniques that may help us understand the nature of black holes. Again, there's tantalizing evidence that it may help us understand the nature of black holes, but it hasn't yet really cracked the real problems in that regard. And it's also been very useful in other areas of physics. As I say, the mathematics has proved to be very useful in a variety of areas of physics.
Okay, so I clearly understand that the mathematical tools developed as part of trying to understand string theory might be super helpful, not just in physics, but also in math. But that being said, what do you think is the missing element that string theory has not yet been able to explain?
Why the universe is the way it is, why we have 4 dimensions, 3 dimensions of space and 1 dimension of time, why the energy of empty space is non-zero and so small, why there are 4 forces in nature, why the elementary particles that we know of are what they are. I mean, all of the fundamental questions in physics, and also literally, how did the universe begin? Those are just a few of the questions that are still open, and they're fascinating questions. That's why, as I say, that's why my book focuses on the unanswered questions, because I try and bring people to the forefront of knowledge so they see what we don't understand as well as what we do. But anyway.
Got it. Okay. I want to dig a little deeper into how did the universe begin, right? So I sort of like to distinguish this into two parts. One is how did universe begin in the sense, how did matter originate, or at least matter as we know it? And even within, sorry?
Go on. Sorry, that's probably the easy question, but go on.
Yeah, but the second part that I'd like to sort of delve into deeper is, let's maybe consider two cells. One is a living cell and one is a dead cell. And if you were to try and break these down into smaller components, we're going to say they're made of molecules, and each molecule is essentially an element, and then you get into the particle physics of it. But what exactly is the distinguishing element between what we call a living cell and what we call a dead cell? What is the element of life?
Well, those are two very big questions. We could spend an hour on each, in fact, both of them are set. Why? Again, I hate to be a constant advertisement for the new book, but one is a chapter. Each one is a whole chapter of my new book, a long chapter. The origin of let's do the origin of matter first, quickly. If you mean just by the origin of why the universe is made of matter, not antimatter, why the universe has stars and galaxies made of matter. That's still an unanswered question, but we've gone a long way towards understanding at least how to address the question and what a likely answer is. It turns out we think that early on in the history of the universe, there were, when it was hot and dense, there was equal amounts of matter and antimatter, and if there had been equal amounts continually, they would have annihilated and just produced a universe full of radiation. But what happened was, by processes we can imagine, although we don't exactly know the details, there was a very small asymmetry produced between matter and antimatter, and then all the rest of the antimatter annihilated with equal amounts of matter, leaving a little bit left over, and that's enough to account for all of the matter we see in the universe. Because in fact, if you count particles in the universe, the particles of matter, protons and neutrons and electrons, are very small compared to the particles of radiation, photons. There's 1 billion photons in the universe for every proton, and those billion photons came from ultimately the annihilation of matter and antimatter. So it's just that little excess that was enough to create all the stars and galaxies we see today. That's a plausible picture. And the question is, the only outstanding question is what caused that asymmetry? Yeah. And there are a variety of possibilities, but none of which for which we have any empirical evidence right now. We're trying to understand how it is. If you go beyond the standard model of particle physics, there are many mechanisms to generate such an asymmetry between what are called baryons and antibaryons. And there are lots of proposals out there, but none of them have yet any, they're all kind of ugly, I will admit, so far, but none of them have any definitive evidence. There's the possibility that the three non-gravitational forces in nature, it's a strong, weak, and electromagnetic force, unified at a very small scale in what's called a grand unified theory, at a scale maybe 16 or 17 orders of magnitude smaller than the size of a proton. And at that scale, new forces would come into play that could create particles where there were no particles before, produce an asymmetry between matter and antimatter. It could also be that there's one sector in the universe that we sort of know of but haven't been able to explore greatly, and that's neutrinos. These esoteric particles that are producing nuclear reactions, because they interact so weakly, it's very hard to measure them. But it's possible that the neutrino sector could hold the key to that. That in the early universe, effectively there were more neutrinos than antineutrinos produced, and eventually certain kinds of neutrinos decayed, producing more matter than antimatter. That's a process called leptogenesis. And that's possible too. And we're looking and trying to measure the properties of neutrinos to see if that's possible. So there are a lot of possibilities, but nothing that jumps out at you as the obvious candidate. And so, at least that's a question we have potential answers for, and we have a methodology of trying to look at trying to understand where to go to get those answers. There are many questions in in nature, or we don't yet know where to seek the right answers. So
Okay.
that's the easy part. Understanding the difference between life and non-life is actually much more subtle than you could imagine, because as I talk about at the beginning chapter, in fact, I just released an excerpt that's on Quillette about the nature and origin of life, how to define life. And it's not so easy. If you think about, life has a metabolism and it reproduces relatively faithfully. As I say in the book, you can think of fire. Fire satisfies all of those things. It turns out life is probably, if you want to understand it, it's a well-regulated mechanism of reproduction that has a thing called homeostasis that can balance balance the rate at which reactions occur, so that reproduction can occur at a well-defined pace. As I like to say, if you look at organic materials and materials in general, they can oxidize. When they combine with oxygen, it releases energy. Rust, fire is the most extreme example, and say rust is another. Life is from somewhere between the two. It's controlled burning, and it's an organized system of organic materials that combine together in bound regions called membranes that can faithfully reproduce and also control their metabolism by homeostasis. Probably that's as good a definition as any. And the best bet is that we went from sort of non-life to life. There were lots of organic molecules around. There are organic molecules in space. The best sort of precursor for complex life is something called RNA, which like what right now is combines with DNA to be part of the genetic replication machinery, and also part of the chemical factory that allows life to happen. Proteins, RNA helps turn the genetic code from DNA into proteins, which then help power the chemical reactions that powers life. And it turns out that it also forms an enzyme, that it can be an enzyme. It can cause reactions to happen that wouldn't happen in it without its presence. That's required for life. Okay. And so the current consensus is, I'd say consensus, the best bet is that the early part of life was an RNA world where there wasn't DNA. And it turns out the basis of RNA, the bases, the nucleotides that are the basis of RNA actually have been seen in comets and other places. And so we're beginning to think of ways and environments where those things can form. And then it turns out, you'd think it's that forming complex molecules is disfavored, in a thermodynamic sense, that, you shouldn't, forming complex things seems to be disfavored. But in exotic environments, like on comets in the presence of ultraviolet radiation, it turns out in certain complex environments, it's been discovered that actually reactions get driven toward forming complex molecules, and that's a real important development, I think, on the road towards understanding the origin of life. We don't know what the first fully biological molecule or organism was. But we're getting closer and trying to understand how you can get an organism that has homeostasis, that has enzymes, that has genetic material and metabolism, and all of those things are. And it turns out they're all related. As I say, it turns out it's not like it's sort of like chicken and egg. It's not like one of them came first. Each of them was related to the other, and so they probably developed in tandem. And I don't know if that issue will be resolved in my lifetime, but we're certainly making great strides.
Interesting. I'll agree that fire and rust might be similar to how we think life is in terms of their ability to reproduce and grow and things like that.
But fire doesn't have a homeostasis. It's not control. It doesn't control itself. It goes out of control. Whereas life makes sure that, if reactions are too fast, then they slow down. If they're too slow, it speeds up. That's the central feature that makes life possible.
Exactly. So what is very evident from this is that chemistry or the similar chemistry is a prerequisite for biology to happen, but biology seems to be something more. And what exactly is that more or the starting
Well,
point?
it's really important that the chemistry of life doesn't happen naturally, because if it did, it would be uncontrolled. It's really important that it requires enzymes. It requires that molecules are required to make chemical reactions occur that wouldn't occur without their presence, because then you can moderate the rate at which chemicals reactions occur to form homeostasis. So it's important that you have a combination of systems altogether that wouldn't be found easily elsewhere. Otherwise, as I say, the burning that happens, that life is controlled burning, and if all those things were ubiquitous, then life will be uncontrolled burning, and it would have utilized all the energy of organic molecules early on in the history of the Earth, and we wouldn't have life now.
Okay, let me park this here and go back to the earlier point that you mentioned. There's the question to ask is, how did the early asymmetry occur between matter and antimatter for matter to overpower the way it is done? So while there could be many plausible processes that could have resulted in this, do you also think all of these processes might require a certain cause, or could they just be at random?
There's no evidence it requires a cause. The processes occur naturally by the laws of thermodynamics, and as the universe cools down. Remember, the universe is cooling down, so that provides a driving mechanism to go out of equilibrium to create things. Okay, the universe is cooling as the universe expands, and that cooling can cause things to go out of equilibrium and produce a system which appears to depart from equilibrium. In equilibrium, you'd have equal amounts of matter and antimatter, but you depart from equilibrium as the universe evolves. So there's no evidence that you need any cause, that anything other than the standard laws of chemistry and biology, in particular, chemistry and physics, would work. The same laws that tell you if you put a drop of liquid in a drop of ink in a glass of water, it'll diffuse. All of those standard laws, as far as we can tell, are adequate in principle to explain the origin of matter. So it doesn't prove there isn't a cause, but you don't need one. It seems like it's an unnecessary additional assumption.
Interesting. But even when you say that all of this happens by the laws of thermodynamics or just the laws of physics as we know it, isn't it true that there's a certain initial condition and there's a certain final condition, and what governs? These laws just govern the process that occurs between the initial and the final condition. So the initial condition is still a prerequisite.
Well, there can be a wide variety of initial conditions, and the laws will allow the regions where those conditions are adequate to happen. It's like, look, it's like on a cloudy day in the wintertime and in the clouds, there are a wide variety of initial conditions, but under some conditions, snowflakes will form. They look quite ordered. They look like beautiful Christmas tree ornaments. There's no cause for that. It's just the chemistry of polar molecules. And so if trying to impose some kind of design on that is unnecessary, and certainly, if you like the idea of beautiful order, look at snowflakes sometimes. So you don't, as long as you have a available energy and thermodynamic evolution, then you'll evolve. And it's true that certain things require certain initial states, but if you have a wide variety of initial conditions, then you'll find that that those states will evolve in regions where those initial conditions exist. So again, you don't need to have any kind of cause or design or behind it, and there's no evidence for that.
Okay, so would it be reasonable for us to extrapolate this to say, and the beginning of biological processes also need not have had some precursors to it? It could just be the natural progression of things.
Yeah, I fully expect that'll be the case. Under the right conditions, life is an inevitable consequence. And I hope that's the case, because then life will be ubiquitous in the universe. But there's no evidence otherwise. Life evolved on Earth about as soon as it could have, given the laws of chemistry and physics. The late bombardment of meteors and comets that were early on in the history of the Earth that would evaporate any early oceans died down within about the first 100 million years. And within a few 100 million years of that, you have the oldest fossilized forms of life. So life appears to have evolved relatively quickly and easily on Earth. We don't know if we're an exception, but certainly there's certainly no evidence that the origin of life requires anything, again, other than the laws of chemistry and biology. It doesn't require any kind of miracle or any specific fine tuning. And instead, life is fine tuned for the Earth rather than the Earth being fine tuned for life. Life evolved under the conditions it could evolve, and who knows in other places whether other kinds of life don't evolve in those other conditions on other planets or other regions of the universe. We don't know enough yet to know about it. It's exciting. It's one of the big unknowns that it's quite exciting that we may learn a lot about in the next decade or two.
Okay. In that case, would you define whatever we define as observable universe to be alive? Do you think the observable universe
no,
could be
I
a
don't
living
see
entity?
that. I don't see any evidence. The observable universe is a dynamical system. It's no more alive than a rock rolling down a hill. It's evolving by the laws of physics, but it doesn't fit any of the requirements. That it doesn't replicate. It doesn't. I don't see it. No, it's not living at all.
Okay. But then, if that were the case, the expansion of universe has to be solely explained by laws of thermodynamics. If it weren't a living
by laws
organism.
of general relativity. I mean, it's you put the evolution of space is determined by the nature of the energy within it, and then as the space evolves, it determines the evolution of the energy within it, and so it's this nonlinear process, and it's a remarkable aspect of general relativity that it can describe the expansion of the universe, and does so very well, so that we can understand the universe back to at least 1 second, and everything we see in the universe is consistent with our simple laws of physics and nuclear and particle physics and atomic physics. And it's remarkable how well we understand the evolution of our universe since the earliest moments of the Big Bang. And I'm shocked in my lifetime of how that development has continued, and especially empirically, things we never thought we'd be able to measure and test, we can now. So it's remarkable.
Okay, maybe I'm switching gears here, but I'm curious to understand. When we say laws of thermodynamics or the law of gravitation, or just about any law for that matter, law is basically something that we know happens, but we do not know why it happens. We don't understand the why.
No, that's not quite true, actually. That's not quite true. First of all, why is a really ridiculous question. It really means how, right? Why implies purpose and that, so it already answers its own question. We really mean how. But we do know some fundamental things, that the law, conservation of energy, conservation of momentum, arise from the fact that space and time have certain symmetries. Have the fact that the laws of nature don't change over time implies that something called energy will be conserved. The fact that the laws of nature are the same from place to place imply the fact that there's a law of conservation of momentum. The fact that, and there are other mathematical symmetries. So we ultimately understand all of the laws of nature to come from mathematical symmetries of space and time, and the internal configurations of matter. So it's not, we don't, now, why those symmetries exist, you might say we don't understand, but that's okay. So they're open questions.
Okay, yeah, so that was
open
basically
questions. As I often say, not understanding something is not evidence of God or anything like that. It's evidence of not understanding. It's an invitation to discover. It's an invitation to discover, and we keep moving forward. And that's the exciting thing about not knowing. That's why the first 3 lines of that book behind me say that not knowing are the three most important. I don't know is the 3 most important words in science.
So I see a book behind you called The Edge of Knowledge. What is it about?
That's my new book. That's coming out next month.
So is it sort of planned and positioned right now for this?
Well, it's I have it up there and it's in the background. I don't know whether it's planned to be up there, but yeah, often I do a lot of conversations and I like to be able to see my book behind it. Yeah, so it's a bunch of, but I have a bunch of them around the office, so I just got a bunch.
Okay, so anyway, back to the discussion on why or how exactly do these symmetries exist in nature. What's even the right direction to look at?
Well, I mean, I've written whole books about this, but it turns out that there's a mathematical symmetry called gauge symmetry that is that appears to underline all of the nature of all the forces, the weak, electromagnetic, strong force, and even gravity are examples of what are called gauge theories that have a certain kind of mathematical structure and symmetry. And that seems to be very, very fundamental in our understanding of the universe. And one of the things string theory tries to do is try to understand how all of those can arise naturally in the context of a mathematical idea. And but we, other than recognizing that they're fundamental to all the forces we know and understand, to try and the question is, could a universe arise without that symmetry in any way? And the answer is maybe. In fact, currently, one of the pictures there are several pictures that suggest that there may be many, many possible universes, each of which has very different properties and different laws of physics. In the most simple versions of the multiverse, gauge symmetry is an essential part of all those universes, but they can still have different forces. But in the string theory, where it's even wilder, there could be 10 to the 500 different kinds of universes, at least if early analyses of string theory is right. It's one of the negative features of string theory. It doesn't predict why a universe looks the way it does. In general, universes should look quite different. But if that is true, then there's lots of different possibilities for types of universes. And it could be, and this is a big could be, that life like we experience can only exist in certain types of universes. And therefore, it's not too surprising to find out that the universe we live in has those properties, because if it were different, we wouldn't be here to ask the question. That's called an anthropic idea, and it could be true.
Okay. So again, I think the question goes back to the same discussion and us trying to ask. Maybe there's certainly no purpose associated for us to ask a why of how the symmetry exists or why a certain law exists. But for the symmetry to exist, the way we try to explain symmetries by laws. And we say that the laws...
laws. We try to explain laws by symmetries. It goes the other direction. Sorry.
Is it certainly unidirectional, or is it also not bidirectional, where we also try to explain the symmetry using laws? How else do we explain symmetries?
That sounds like semantics. No, as far as we can tell, all the laws of nature arise from fundamental mathematical symmetries, and we don't apply laws to derive those to derive those symmetries. So generally a one-way street.
Okay. So how do you think about the directionality of time?
How do I think about it? Sometimes I'm happy about it, sometimes I'm not. It's a strange fact that time seems to have a direction where space doesn't. Now you can go around in a circle in space, and you can't in time. And general relativity unifies space and time. So people are often asked the question, why can't we go back in time? And the answer is we don't know if you could or not. You can write down mathematical spaces. You can even produce systems like wormholes that would allow time travel. We don't know if they're physically possible. So the directionality of time is maybe fundamental to nature, but we don't know it. Now, time, of course, is a very subjective quantity, and in the sense that while it's a fundamental parameter that describes how the universe evolves, different observers will measure different times, and so again, you're anticipating my book, because the first chapter of my book is about time, but the whole question of whether time is even fundamental remains an open question in some sense. To me, it's kind of a less interesting question, because if time is an illusion, that's fine, but if you miss the 5 o'clock train to get home, it has an impact on your life. So time is very real for all of us, but whether we can understand whether the directionality of time is built in fundamentally to nature is not at all clear. Certainly in general relativity, it doesn't have to be. General relativity allows lots of systems where you can do what are called closed time-like curves. We just don't know if they're physically accessible. And in the case of a black hole, when gravity becomes strong, time is affected by gravity. We know that, we measure that. And when you get near the event horizon of a black hole, then for an observer outside, it looks like someone falling into a black hole. The time stops. They freeze at the surface of the black hole because there's an infinite time dilation between those two. But when you go inside, fall inside a black hole, what space becomes time-like and time becomes space-like. So the sort of relationship between time and space flips inside a black hole. Space has a single sort of unidirectionality. You always are moving towards the singularity, never away from it. No matter what you do, you're always moving forward in space and inside of a black hole. So that space has a very time-like character inside of a black hole, whereas time is the opposite. So in general relativity, it remains an open question about the nature of the forward direction of time. Certainly in our universe, what's been recognized is that the laws of thermodynamics do provide some natural forward direction. Again, if I drop a bit of ink in water, I see it diffuse. I never see it come back and form the ink, and that gives a directionality. So if you watch a film, you can clearly know where of an ink drop, and the films run backwards, it certainly seems unnatural.
Okay. I've been having a strange thought. It could be completely stupid, but I want to ask it anyway.
Okay.
We say that the expansion of universe is accelerating. Now, is it certainly so that the expansion is accelerating, or is it possible that our experience of time could be decelerating, much like the scenario that you mentioned within how space sort of takes the role of time in black holes?
Not really. It's accelerating because we can measure time effectively in other ways, by measuring atomic processes in spectral lines and other in systems. So we can check to see if the laws themselves are changing in strength as we go out in the universe. And so the acceleration of the universe it appears to be a real acceleration. And not only that, it's kind of required. There are lots of independent directions that suggest it should be happening. In fact, in 1995, before it was observed, a colleague and I argued it should be the case because of other arguments, measurements we make in the universe. So there's no. There are good ways to test that the universe is more or less the same everywhere, and that the laws of physics are the same and not changing from place to place, and that would be required to produce this kind of mimicking acceleration.
Okay. What's one question that still keeps you awake at work today, Professor Krauss?
There's a whole bunch of questions. What's the origin of life? Are we alone in the universe? Is our universe unique? Those are grand questions. Other questions is, why is the dominant energy in the universe reside in empty space? What is the nature of dark matter? Something that's occupied a lot of my scientific career. There are a host of, every day there are new questions.
Do you ever wonder, why is it that with the phenomena of life possible, why do we have this phenomena of curiosity?
Well, that's an evolutionary question. Curiosity presumably has been useful evolutionarily to humans, or it just could be an evolutionary accident, like our ability to do mathematics. But I suspect curiosity helped early modern hominids survive in the savanna of Africa. For example, if the leaves rustled and you didn't wonder whether that signified something, the early hominids that didn't wonder that tended to get eaten by lions, or predators. And whereas if you assume that perhaps there's some reason the leaves are rustling, you might act in a way that would lead to your survival. So seems quite reasonable. It has an evolutionary purpose.
Okay, and one last question. This is something I asked to everyone on my podcast. What would you do today if you were a 22, 23-year-old graduate?
If I was a graduate today, what would I do?
Yeah.
Well, When I was younger, I thought of going into biophysics, but it wasn't a very interesting area. But I think right now that there's the frontiers of biology are very, very exciting. At the same time, if you're a physics student, it's a golden era in some sense in understanding the universe, but also in areas of trying to manipulate quantum mechanics, quantum systems like quantum computers to develop new ways of new types of materials, and of course new computing technologies. So those are all exciting areas that I would consider going into myself. Particle physics per se is in the doldrums right now, but it's still from a philosophical perspective fascinating. What are the fundamental forces in nature? But the answers we may get by looking at the universe, which is why, as a particle physicist, I first moved into cosmology, because I thought that was the most fruitful way of answering those questions. But genetics, biology at a fundamental level, genomics, and as I say, in applied physics, quantum computing, understanding quantum mechanical processes and quantum mechanical materials are certainly two growth areas, two big important areas. Making better batteries from a point of view of an engineering might be a useful thing for the world as well. Look, you never know where the greatest breakthroughs are going to come in, and that's the great thing about science. It's like 1,000 points of light. You never know in your fundamental research where the breakthrough is going to come from. So as I like to tell people, if I knew what the next big thing was, I'd be doing it now.
Right. Thanks a lot for being on my podcast, Professor Krauss.